So our next speaker is Karol Hausman. So he's a staff research scientist at Google DeepMind and an adjunct professor at Stanford. So I think he brings some much needed industry perspective here, given all the strides that industry is making with these massive large language models that are typically out of reach of a lot of the academic labs. So yeah, please join me in welcoming him.
All right, everyone, I'm Karol. I wanted to tell you a little bit about language as a connective tissue. That's a work done by a lot of people at Google DeepMind, and it's probably the last talk of the conference, so I'll try to be quick. So I wanted to tell you a little bit about how my thoughts around language have evolved over the last year or so, and I was thinking last night what would be a good introductory slide that would kind of get that message across and really convey my excitement about this area and how the field has changed. And I finally figured it out. So I think LLMs are these marvelous artifacts that if someone showed them to you even a few years ago, you wouldn't have believed that this is possible. And you can think of them in many different ways. You can think of them as these like autocomplete, like slightly better autocomplete machines that don't do that much. They just predict next word and that's it. But you can also think of them as these general pattern recognition engines, these general meta learners that we always wanted, that can recognize patterns and latch onto them really quickly. You can think of them as something that maybe tells more about our intelligence than the technology itself. You can think of them as world models that maybe look at the world through the lenses of text and language, but world models nonetheless. And as with any technology, there are some skeptics and there are some enthusiasts of large language models. But I have a little proposal for all of you. If you are a skeptic, if you don't believe that these are actually marvelous artifacts and they have all these things, all these properties, for the next half hour, let's just force yourself that you do think that, all right? So for the next half hour, we give ourselves the permission to think that LLMs are these incredible machines that will keep on getting better, that are these general reasoning engines, and it's our responsibility to take advantage of that as much as possible. All right, deal? All right. And after this half hour, we go back to our own beliefs and we can complain about them and say that they don't understand the world and so on. But for this half hour, we embrace them. Okay. So I haven't put that much thought into language before LLMs happened, but I had a few thoughts around it. One is that it's this really nice, compositional, efficient, robust medium that allows us to communicate fairly well. I also thought that it's really nice that if we incorporate it into some of our models, it makes them automatically interpretable, at least to some extent. The robot can tell you what it's currently thinking. It can express it in natural language. If we have a language interface, we can communicate with that robot naturally. I also thought a little bit that it's cool that language is abundant. It's everywhere. I didn't really fully internalize this. I think I internalize it now much more with LLMs. But it's cool that everything out there is written in language. But there are a few things that I only internalized after LLMs happened. And one of the properties is that language also provides this universal API that we don't need to agree on in advance. Right? So we often talk about different parts of robotics and how they are all connected. And it was never clear to me, how can we agree on the interfaces between all of these different components? Are we sending segmentation maps? Are we sending some embeddings? If so, who is training those embeddings? And how can we all agree on the embedding we want? And what are these representations? But the nice thing about language, and we can see this today in real time, is that we didn't have to agree on that, and everybody is using it. We have text-to-image models. We have text-to-video models. We have vision language models that can describe the scene in language, that can do segmentation in language. And it provides this connective tissue, this canvas, that connects all of these different components, which is really, really nice. And then the other thing that is connected to that is that language in general allows us to communicate between all kinds of different things. And even if you look at us, it's the thing that connects all the different areas of science, of entertainment, everything else, all the different areas of life where we can exchange information and understand how all of these things are connected, which is really, really cool. And I think something like this also translates to models, tools, where these models can communicate with each other, can invoke each other, can use each other as tools, and so on. So I started looking at language as this connective tissue. And we see some examples of that with large language models today, with some interactive agents. So this is a screenshot from this paper from Meta called the Tool Former, where we have a language model that writes some text, but rather than relying on the knowledge that is embedded in its weights, every now and then it invokes a certain tool. And it knows which tool to invoke based on just the knowledge that it has in it. So it writes a part of text, like for instance, the New England Journal of Medicine is registered trademark off, and then it invokes a tool that will actually give the right information and fill in the gaps. It can also use a calculator, it can use maybe wiki search and things like that. It's kind of like asking different experts to fill in the gaps, and then the language connects all of these different components and makes sense out of it. We also start seeing this in interactive agents in different startups, such as Adept, where one of these components that the language is connecting is the component that actually executes actions in the virtual world, where you can just type, book me a trip somewhere, and it will figure out how to query a website to get the information from there, and then how to invoke different tools to take the right actions to book the trip for you. So since we are trying to embrace language in this half hour, let's imagine what would it look like if we took that idea of language as a connective tissue and translated it to robotics. So we'll try to put the language at the center of everything in robotics, and we see where we get. So this is a simplified map of how you can view robotics today. So this is how we traditionally would look at it. So at the center of it, maybe you would have some kind of traditional planner that will kind of take into account all the different sensory observations and decide what you should be doing next. Let's say that one input to it could be a task, maybe expressed in natural language originally, but then it would actually need to be translated to some planning language, like PDDL or something like this, so that we can do all kinds of logical operations on it, so that the planner can use it. A planner like this would also need to take into account the state of the world. Traditionally, the way we would do it is we would maybe build a map of the environment using SLAM or something like that. And then the planner would need to take into account what the world looks like, where you are in that world, and use that to generate a good plan. And then we would also need to take into account the state of the robot, right? Where the robot is, what are maybe the joint angles of the robot, what's in its gripper, and take all of that into account to generate a plan. Then that plan would take all of that information into account and generate a policy. And that policy at the end will generate actions. That policy could be learned, doesn't have to be learned, it could be represented in many different ways, but that's more or less, that's one way you can view robotics today. So let's take this picture and let's try to replace some of these interfaces with language. So rather than having a traditional planner, we'll have an LLM at the core. It will be at the center, it will take all the information into account and reason about everything in language. Then the task will be just communicated in natural language. You can just express exactly to the robot what you want, and the planner would be able to take that into account. The world state could be also, does that work? There you go. The world state could be also expressed in language. You can have some kind of component that can look at the scene, maybe remember what it explored before, and just tell you what is happening in the world. Maybe there is an apple in the drawer, there is an orange in the drawer, the top drawer is open, and there is nothing on the table. There could be multiple different components that describe the world state to the language model planner, but all of this is communicated through language. The same with robot states. Rather than describing the joint angles exactly, we kind of go one level of abstraction higher, and we just tell the planner, there is a banana in the gripper, or the robot is near the cabinet. And you can notice that these pieces of information are not as specific as they were in the previous picture, but they could be useful nonetheless. So then LLM Planner can take all of that into account, can reason in language, and it can then tell the policy what to do next. And it could tell it also in natural language what you should do. and then that policy will lead to an action. All right, so let's go with that picture. We are embracing LLMs in this session. Let's do that. So I'll tell you about some of the components that how we actually try to make this picture and reality and see how it goes. So we started with the core component, the LLM planner. And there are in a few talks today, people mentioned this work, but I wanted to briefly talk about it. So we wanted to use LLMs for planning, so we started playing with them. So we took 3 LLMs and we gave it a task, like, I spilled my drink, can you help? And one LLM said, you could try using a vacuum cleaner. The other one said, do you want me to find a cleaner? And the third one was apologetic about it. Not super useful. So the immediate problem we run into is that our robots can only do a fixed number of commands and LLMs don't know about it. So they don't speak the right language, right? So we need to get them to speak robot. But then there's another problem. If I ask you, I spilled my drink, can you help? And then you open your eyes and you see that there is a sponge in front of you, you would kind of immediately know what to do. There's a sponge, I should probably give you that sponge. That would help. But the problem is that LLMs are not really grounded. They're not grounded in the real world. They can see, but even on top of that, they don't really know about themselves, right? Like, they don't know what embodiment they're in. They don't know if they're a robot right now. They don't know if that robot has hands. They don't know that even if that robot had hands, does it know how to grasp these things? So we need to ground these LLMs in robotic affordances. They need to know what is possible in the world. They need to contextualize their knowledge. So this is how Seikan came about. So it works fairly simply. You ask it, for instance, please put an apple on the table, and then you prompt it with I would 1. And then rather than using the LLM in a generative mode, you would use it in a discriminatory mode, where you would list all the different things that the robot is capable of, all the different tasks, and then you would ask the LLM to score the likelihood of those. So the first part of this would basically tell you what is currently useful, what LLM thinks that is semantically meaningful. So we can score all these different options, and initially it would think that picking up an apple would be a good thing to do. But then we need this other component that looks at what the robot is currently seeing and takes into account all of the robotic experiences and knows a little bit more about the affordance. And if the robot opens its eyes and it's in the middle of nowhere, there is no apple to be picked. So instead, we can score the image based on everything that the robot has experienced so far. In this case, we're using a value function that's trained with reinforcement learning and can tell you the probability of success given all of its experiences and given the current image and the language command. Now, taking these 2 into account, we can combine these and see that the action that we should actually take is to find an apple first. So we're combining kind of the usefulness that comes from the LLM and what is possible that comes from the affordance function. And the combined score tells us what we should actually do. All right, and then we can keep doing that. So then we generate the first step of the plan, the robot executes it, and we keep on going. So this is more or less how it works. Here's a little demonstration. So we have a robot. This is the situation that we were faced with. Somebody spilled a Coke. So you can type, I spilled my Coke on the table. How would you throw it away and bring me something to help it clean? You can type it many different ways. LLM should be able to parse it. And you can see that here on the right, you can see that there is 2 components. There's the language component and the affordance component, and they're both scoring different options that are available to the robot in the skill library. So you can see what language thinks is possible, what affordance thinks is possible, and a combined score. And you can see that sometimes they disagree, but usually the combined scores leads to something useful. So you can see all the different steps that the robot is going through, such as I would first find a Coke can, then I would pick it up, go to the trash can, put it down, so like throw it away, then find a sponge, pick up the sponge, and go to the table, and then it drops the sponge, I believe, and it's done. And interestingly, it doesn't wipe the table, right? Like, it just leaves it to the user. And that's because the affordance function knows that it's not really, it doesn't know how to do it, right? So you can view it as, well, we don't have the right skills, but I think the nice part about it is that if you had a wiping skill, you can add it to the library, and as long as there's an affordance function, then the language model will take that into account. And if it doesn't have it, then it will just give up and leave it to you. But it has the awareness of what it's capable of. All right, so this is how Sekan works. But I think the most exciting part about it is actually what happened after we initially published it. So we switched Sekan to what we call now Palm Sekan. So initially we were working with a language model that was a little bit smaller, that wasn't that performant, called Flan. And at some point there was this better language model that came out. Whoop. So we swap out the language model and kept everything else the same. And what we noticed was quite interesting. So this is the performance of Flan that we had initially. And as soon as we switched to a better language model and then tried different sizes of that language model, the performance of the planner started improving and the robotic performance started improving. And since all of us work on robots, you know how difficult it is to improve robotic performance ever, right? Like whether that means collecting more data or spending a ton of time and putting a lot of engineering effort, it's really, really hard to improve robotic performance. But here you can just kind of swap out the model and kind of ride the wave of the benefits that come with that. And it's not just the pure performance, but we also get these new features. For instance, now with this new model, we can use this technique called chain of thought prompting, where before, if you ask, say, how would you bring me a fruit that is not an apple, it will pay so much attention that you said apple, that it will definitely bring you an apple. But now with chain of thought prompting, it can reason through its steps. It has this more powerful language model at its disposal, and then figure out that it's actually not an apple that you want and bring you the right thing. And now it can also do all kinds of queries. It can do queries that are really abstract, like I'm thirsty. Queries that involve a little bit of arithmetic, like bring me 2 different sodas. It needs to understand what 2 means, what the sodas need to be different. It can also do some long horizon things, such as I left out a Coke, apple, water, can you throw them away and bring me a sponge to wipe the table, or multilingual queries, emojis, and all kinds of things. And we get all of that for free. You can also play with it yourself. If you go on the Sekan website or you just copy that link, there is a little playground that you can play in simulation and see how Sekan works and explore it a little bit yourself. All right, so we talked a little bit about the core element, the LLM planner, but let's go forward. Let's see how we can change other components. So the other components I would focus on is this world and robot state understanding. And if you paid close attention to Sekan, you might have realized that there is a big problem with it, which is that we don't really close the loop here. So if we generate a plan, like for instance, bring me a drink from the table and the robot starts generating the plan, if at any point that plan fails, for instance, we don't pick up the Coke, we just failed at it, the plan will just continue. The robot is not aware of that and it will just keep on going. So we need to have some way of informing the LLM that something went wrong. So that's where we introduce inner monologue. So here's the idea. We have our little dialogue, our little plan that was generated by, let's say, Sekan. And then at any given point, there's other actors that can interject. And these actors will be also communicating in language. So let's say you have a scene descriptor that is a vision language model that can look at the scene and tell you what it sees. So for instance, it can tell you, well, I see a Coke and a lime soda on the table. And then you can have a robot that then responds to that and take that into account. They all exchange this information in natural language, and it can ask a human, what kind of drink would you like? And then the human says something with caffeine. And then the robot decides to pick up the Coke, and then it can invoke yet another actor, which is a success detector that also communicates in natural language what is happening in the scene. And it says that you failed at picking up Coke, so then you can adjust the plan accordingly. And what's interesting here is that you have all these different actors. Maybe they also include human that can interject at any point and tell it how exactly they want the task to be done. But it also allows us to bring in all these different models that keep on getting better, that can exchange information in natural language and have this dialogue that leads to successful execution of a task. So here's what it looks like at the end. So let's see if that loads. All right, so we have a few different actors. We have a human, we have a robot, we have a scene descriptor, language model, and a success detector. And they can all speak in natural language. So the human asks, can you bring me a soda? And then we have a language model that generates the first step of the plan. For instance, find a Coke, then pick up the Coke. And then we have an adversarial humans that come in and move the Coke away. But now the language model can invoke a success detector that looks at that scene and tells it whether the action was successful. So it says in natural language that action was not successful, and then LLM decides to invoke a scene descriptor to see what is happening. The scene descriptor says that it can see an orange soda, so then the LLM can ask a human that there is no Coke, there is an orange soda, is that okay? The human can respond in natural language, and it can go find the lime soda and continue the tasks. So we have all these different actors exchanging information in natural language and talking in this abstract way about what is happening, and that allows the robot to execute the task. All right. All right. So I'm actually going to skip that part, but we can also talk a little bit about how world states can be represented in different ways. But instead, I wanted to tell you about the part I think that is the most controversial. So I think at this point, more or less, a lot of us agree that for high-level planning, language could be a really useful medium, right? Like it's a really nice interface. It allows us to express things in a very natural way. It also allows us to plan in this continuous space and reason about all the different intricacies of real world, and we can use the common sense that is somewhat embedded in language models for high-level planning. But a lot of criticism, or I guess like the main issue with robotics is not really the high-level planning. It's actually doing the thing. And it's actually running the thing on the robot and getting in touch with the world, and can LLMs help here? So let's see. So is language only useful for high-level planning? So the thing that we use that makes this high-level planning useful is the intuition and common sense that is embedded in large language models. But the intuition and common sense is not just a high-level thing. It applies to low-level behaviors as well. And this behavioral common sense, I would argue that this is actually the dark matter of robotics. This is what we are all after. So examples include the spatial understanding, like if you ask a robot to move a little bit to the left, what does move mean? What does a little bit mean? What does to the left mean? Temporal understanding, like move faster. What does it mean exactly? How do you translate that to behavior? Or this functional understanding, when you just ask a robot to balance yourself and can translate it to all kinds of different commands. And I would argue that those things seem like something that should be stored in LLM weights, all right? If you play with these LLMs, you start realizing that if you ask for any of these things, they can actually do pretty well. They understand what you mean. They understand how to execute something like this. So here's an example that I tried last night when I asked, can you pick up a credit card off a table? And I prompted with your robot and just try doing that. And here is a plan that ChatGPT came up with. It said, here's a succinct strategy, and it says, assess the credit card position, position yourself and your gripper near the card, align with its edge, slide the credit card gently along the table edge towards your gripper, then gradually position your gripper's edge under the credit card, allowing it to rest on the gripper surface, then lift the credit card carefully, and so on. So it figured out that you can slide it off the table, get it off the edge, and that would give you enough space to actually grab it. And if you keep on prompting it, it actually starts coming up with all kinds of different solutions that are really creative. Like you can apply a little bit of force to the edges of the card that makes the card bend over. And when the card is bent, you can grab it on the side. So it seems that it has a lot of knowledge about the slow-level behavior, how to execute these tasks. But the question is, how can we extract it? And actually, I don't think we have great solutions here. And I think that we can probably do a lot more work and a lot of creative work on how to get it out of those weights. So one way we propose to do that, or we tried it, and I don't think that is the way, but I think that at least shows that it's possible, is to leverage the fact that language models can write code. So we can ask it to balance a card pull, and it can generate a pretty good code that uses PD control and can define all kinds of different coefficients. If you prompt it a little bit more, it can also generate impedance controller. And if you run it, it actually ends up balancing the card pull. And you can try it with all kinds of different things, and it seems to be pretty decent at that. So that's where we introduce code as policies, where we can use perception and control APIs to let LLMs generate code without any fine-tuning. And it seems to work for simple tasks. So it can leverage It can perform arithmetic operations and write feedback loops. It's much more expressive than something like say can. It can leverage APIs. It can use NumPy, all the different libraries that you would use. And it also read all the robotic textbooks that you read. So it knows about all the different control strategies and different ways to accomplish tasks. And here we also introduce this hierarchically generate new functions, which is kind of a detail. But at the end, it can do all kinds of different things, such as move the blue block to the topmost ball. It needs to understand what the topmost ball is and do some math to get there. It can also do things such as wait until you see an apple. It can use if statements and for loops, something that would be basically impossible to express with natural language using SayCan. And it can also move the blocks in a horizontal line near the top. You can kind of understand how much ambiguity and intricacies of language is embedded in that sentence, right? What does near the top mean? What is a horizontal line? How perfect does it need to be? And can use all these different libraries to reason about it in code and then generate the right actions. So yeah, at the end, we can generate quite a lot of different behaviors. And it's also not embodiment specific. So we can run it on these top-down scenes, but we can also run it on the robots that you've seen before, where you can ask it to put apple and cocan in corresponding bins, or you can ask robots to draw things, and it will generate code that is accurate for that embodiment. All right, so a few takeaways. Leveraging foundation models can allow us to scale. I think we have this tendency of thinking about this as something that is trivial and that kind of makes us look like we're just jumping on the bandwagon. But I think there is actually quite a strategic importance to doing that, and I'll talk about it in a second. Language, I think, is much more than a nice interface, and large language models are much more than these like very simple machines that can tell us a little bit about high-level planning. And I think they have much more information in them that we can really leverage for even for low-level control. The bottleneck is still on the low-level skills, and I think we all realize that, and I can't emphasize that enough, and that's where most of our work goes. Work such as RT1 that we presented at this conference and other directions. But the point that I really wanted to drive home is that it's actually really strategic and important for robotics to put these large language models and vision language models at the center of robotics as a field. And to drive that home, I like this analogy to a bitter lesson. So bitter lesson is this famous essay from Rich Sutton that basically says the following. The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. And the ultimate reason for this is Moore's law. So basically the reasoning here is that if you can, it doesn't necessarily say that we shouldn't work on AI algorithms. It just says that the AI algorithms that leverage this trend that is happening outside of AI, which is Moore's law, we are getting cheaper and cheaper compute. These are the methods that will prevail because they kind of can ride the wave of improvements that is happening outside of AI, and these are the ones that end up working the best in the long run. So I would like to propose bitter lesson version 2, bitter lesson for robotics. So we'll meet here in 70 years from now. This workshop will keep on going. I'll look a little different. And I would say then that the biggest lesson that can be read from 70 years of robotics research is that general methods that leverage foundation models are ultimately the most effective ones. And I feel like foundation models is something that will keep on improving regardless whether robotics uses them or not. This is a similar trend that we were seeing with Moore's law, that it's completely independent. And if we can position our methods so that we can leverage that trend and ride that wave of improvements, these are the methods that will prevail. All right, we can all go back to being skeptics about LLMs now, and thank you so much.
All right, so how much do you think this is about language versus just this being like a really good expert system? in the sense like if you go back to the 90s, they told us that expert systems were great, and then we told them that they were dumb, and now this is kind of an expert system, right? So is it like if we had a different way to train a different expert system, would it kind of do the same thing, or does the structure of language matter here?
Yeah, I think maybe a controversial opinion is that these language models actually don't have that much to do with language. I think it just, they happen to be trained on language because we have a lot of it and it's kind of like a closed set. But once they're trained on language, they become these general meta learners. And we've seen it in previous talks, like what Dorsa was showing with the work from Suvir, showing how it can quickly latch onto patterns, even though it's a pattern represented in numbers or in some kind of symbols. And it doesn't really look like language. It can just really quickly recognize a pattern and continue with it. And I think just we happen to train it on language, and that's what gave us that kind of property. But at the end of the day, it doesn't have that much to do with language. It's just like a great meta learner.
Cool, thanks.
Really great talk. I was just wondering, what do you think it's going to take to build a skill library that can change on the fly with these transformer architectures?
Yeah, good question. I think the honest answer is I don't know.
Sure.
Yeah.
Any speculation is fine.
Yeah, if I were to speculate, one way to go about it is just to keep on scaling up and keep on adding data and keep on leveraging vision language models and bringing knowledge from those models to robotics. I think another way to think about it is to leverage the meta-learning properties of these models. So cast the problems so that we can leverage the fact that they can latch onto patterns, and maybe as they have longer and longer contexts and they can do in-context learning better and better, maybe that's eventually how we'll get generalization to new skills that we've never seen before. So you can imagine if vision language models would behave the same way as language models do today, and they have enough context that you can just prompt them with a single demonstration or an episode demonstrating what you want the robot to do, maybe that would be enough to like latch onto that concept, ground it in the real world understanding that that model got from all the pre-training, and then it can carry on. But yeah, that's a wild speculation.
So one thing that I'm curious about, and this may be a misguided opinion from me, but the thing that the language models seem to struggle with right now is like an internal consistency and grounding and et cetera, right? Do you think that this is because you're pushing the limit of what you can do with this stuff regardless of that, right? So like, do you think that's actually like a real issue that we'll have to address at some point? Or do you think that we can address it by looking at it externally, right? Like you produce these plans, can you then use something else to look at the plan and see whether it's valid and then?
Yeah, so that's a good question. I'm not sure how big of a problem it is. I feel like if we assume that the trajectory of these models continues, if they keep on getting better, and from what we've seen so far is that we can argue whether they're good, whether they understand the world, whether they're consistent, but I don't think we can argue that they're getting better and they're getting repeatedly or rapidly better. They're getting better at a faster and faster rate. So my prediction would be that in a few years, and that is happening outside of robotics, regardless whether we use them or not. My prediction would be in a few years, some of these issues would go away, and then maybe it doesn't matter as much what particular technique we use to accommodate for them. But I think there's a lot of works out there already that show how you can translate it into different language and maybe use planning language or something like that that makes them much more consistent. So even with all of these problems today, I think they're still being quite useful.
Last call for questions. Okay, all right, let's thank again.